For the molecular shape and bonding section, this is going to be just a short review on reminding us things about how to name molecules and how to do Lewis structures. Note that this video by itself won't be enough to cover every single type of structure. The goal for this is to listen and see, okay, do I remember how to do Lewis structures? And when he mentions things like these shapes or these bond angles, do I remember them? If you don't, you want to go back to your notes or go back to an online source and check out what all those were. Because I'm not going to cover every single shape, but I'll do a series of examples. So you can see if you remember how to do these problems or not, and what your memory is like for shape and bond angles. So this first one I suggest, just like on the last video, try these questions first. Try telling me the molecular shape for these molecules and calculating their bond angles before listening to me go over each of them. Okay, so hopefully you paused it. If not, I recognize you're in a hurry. You may still just listen to this part. So let's look at each of these molecules. I'm going to answer both questions at the same time. Let's start with CH4. As we remember, hydrogen can't be a central atom, so we know C is going to be in the middle. Then we're going to bond it to 4 hydrogen atoms. And then we're going to compare how many electrons we've drawn to how many valence we have. Carbon provides 4 valence electrons. Each hydrogen provides 1 for a total of 4, so we have 8 valence. And from that, we've currently drawn 4 bonds, and each bond represents 2 electrons. So we've drawn 8, which gives us 0 electrons remaining. So we don't have to draw anymore. This molecule's done. Remember, for each of the shape questions, you're going to need to draw your Lewis structure first, because you need to know where lone pairs go to know what your shape's going to be. So the shape for this will be that this is a tetrahedral molecule. Now for the next question, what are the approximate bond angles? The bond angles for a tetrahedral molecule are going to be at 109.5 degrees. Remember, this is the only one that doesn't have sort of a round number, so you have trouble remembering it. I just remember that tetrahedral is 109.5. It's the one that looks a little different. All the others are going to be round numbers, like 180, 120, or 90. But this one case is going to have the one where it's a little bit different. This is because, if you remember, the 4 atoms aren't in the same plane. In our other shapes, everything is either in a singular plane, such as in linear or trigonal planar, or it's in 2 planes, such as with our square bipyramidal, where you had both the axial and the equatorial planes. But for our tetrahedral molecule, they're not all going to arrange neatly into 1 or 2 planes like that. So the angle's not going to be nice and evenly divided up. So we've got our angle, and we've got our shape for this one. So let's go on to the next one, BH3. Again, hydrogen can't be our central atom. So we have boron attached to hydrogen, attached to hydrogen, attached to hydrogen. Here, we count, we've got 6 total valence electrons, 3 from the boron, 3 from the hydrogens, and we've currently drawn 3 bonds. This is another case where we don't have any extra electrons. This may look strange at first, but you have to remember boron was one of our exceptions. It was okay for boron not to have a full octet. So in this case, we have a total of 3 electron domains, our 3 bonds, and we have no lone pairs. That's going to give us the shape of trigonal planar. Now we've got a question of, so what are these angles between this HBH bond, the HBH bond? You can either just remember it's 120 degrees. The other thing I think about is, because it's in a singular plane, we have a circle. And that circle has to be evenly divided up. So if I'm going to evenly divide up a circle into 3 sections, since a circle has a 360 degrees total for its angles, each of these is going to have to be equal to 120 to be able to get a full circle once you have 3 of those angles. So if we do 360 divided by 3, we do indeed get that this is a 120 degree angle for each of these angles. So now let's look at something where it isn't just a case of we've got exactly the right number of electrons without having to draw anymore. Let's look at SO2. So for SO2, S is our central molecule. We're bonded to 2 oxygens. We know we should have a total of 18 valence electrons, and so far we've drawn 4. So we have 14 left to go. If you remember, you start by putting electrons on your external atoms before you put them on your central atom. And we're going to try to get everybody to 8. So, 6, 20. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we've drawn 12 electrons. We've got 2 remaining. we will draw 2 on our sulfur. So, right now we go and we check, are all the octets filled? Well, the 2 oxygens are, but our sulfur isn't. So if we remember right, the sulfur is going to have to borrow electrons from one of the oxygens to be able to get to 8. So let's take one of these lone pairs and turn it into a double bond here. So here we're going to end up with S double bonded to this oxygen. We have 1, 2, 3, 4. And then a single bond to this oxygen. 1, 2, 3, 4, 5, 6, 1, 2. Now remember, in case it comes up, you also may have to worry about resonance structures at some point. So here, it could have been either double bond in this case. So we also could have gotten S, double bond O, single bond O, where we drew the double bond in a different location. And that this would be a perfectly okay shape as well. So both of these resonance structures are okay. But for figuring out the shape, they're both going to have the same thing for us to worry about. So we know we are bonded to 2 atoms, and we have 1 lone pair. That gives us a total of 3 domains. So we have 3 electron domains, which means if the question asked you for the electron geometry only, it would be trigonal planar. But in this case, we ask about the shape of the molecule. And over the molecular shape, while the lone pair has an effect on the shape, we're going to, in terms of naming it, we're going to act like it's not there in terms of what shape it makes. So when we make an SO2 molecule, we're going to end up with S double bonded to one of our O's, single bonded to one of the others, and we've got this lone pair up here. We end up with a bent shape here. So let's do all this. So we end up with the bent shape because we only worry about naming the shape from the S, the O, and the O because those are the atoms in our molecule. This lone pair still has an effect on where the electrons go, so it pushes the atoms so we don't just get a linear shape, but the name itself comes from where all the atoms are positioned. So this is going to be called bent. We can also know that the angle is going to be close to 120 degrees because it's similar to a trigonal planar. But importantly, it's specifically going to be less than 120 degrees. That's because this lone pair here is going to be able to push our atoms closer together so that this angle ends up being slightly less than 120 degrees. So therefore, if you had a problem that asked you to compare the bond angles of SO2 and BH3, our SO2 bond angle is going to be smaller than BH3, even though both have a trigonal planar electron geometry, because in this case, the lone pair pushes that angle to be slightly smaller. So that's the case where you have to start worrying about the less than sign. If it just wanted to know approximately what the angle is, it would be 120. But it's going to be slightly less, and you can't know just from looking at exactly how much less. That's something you're going to have to measure or do some more with. There's not an exact equation for us for the purpose of this class to quickly know, oh, that's 119 or 119.5 or 118 or something like that. You can just say it's less than 120. So let's look at another molecule. Let's look at SF6. So here we know sulfur is our central atom. We've got a total of 6 fluorines. Note, I'm not drawing the dashes and wedges to help us with the shape name. That's okay if you do that as well. But this is just to be a quick structure when I'm not sure what the shape is when I'm first doing it. So SF6 has a total of, let's see, how many electrons do we have? We have 7 times 6 for the fluorines, plus 6 for the sulfur. We should draw a total of 48 electrons. So we'll start drawing, we'll add 6 to each fluorine. At first, because remember we're filling up the external atoms first, and we're going to see if that uses all our electrons up. I'm doing my best to draw these. This pen likes to bring up a menu if I draw the dots certain ways. So let's see. We drew a total of 8, 16, 24, 32, 40, 48 electrons. So we've got all the electrons we need. And from this, we should know that the name of our molecule is going to be octahedral. And that our angles in an octahedral are going to be 90 degrees. That includes both the bond that occurs right here between the axial and the equatorial plane, as well as the bonds right here in the square that's formed by the 4 fluorines that are that are inside both fluorines are in the equatorial plane. It's a little bit hard to draw on a flat background like this, so if you have some trouble getting how those shapes would work, I suggest you honestly use Google or some other type of search engine to look up pictures of like an octahedral molecule, and they can do a better job of drawing it than I can with my pen. Okay, so that gets us that shape. So let's look at another molecule. Let's look at PCl3. So we have PCl3. We're going to have our phosphorus in the middle, and we're going to have 3 chlorines. I don't know how many lone pairs there are yet, so I don't really know what shape, how I'm going to try to organize this. So that's why I don't like to try to start drawing them in like a T shape or in a trigonal planar shape or anything like that, because I'm not sure how it's going to be arranged. So I know I have a total of 7, 14, 21, 26 valence electrons when I add them all up, and we've currently drawn 6. So I've got 20 left. So first we fill up our chlorines because they're our external atoms. From this, we're going to use up a total of 18 of our leftover electrons, and we have 2 left over. So that's going to go on our P. So that tells us if it asks the electron geometry, that would be tetrahedral. But if it asks us the molecular shape like this problem did, this is going to be trigonal pyramidal. Again, if you don't remember this and can't see it from there, you're going to have to go back and look at your list of shapes. The trigonal pyramidal shape comes from the fact that there are 3 bonding domains and 1 lone pair domain. It also asks what's the approximate bond angle. We know that it's going to be less than 109.5 degrees. That's because a tetrahedral electron geometry has angles of 109.5. And again, we have this lone pair that's going to push the chlorines together. So because it's got more space, so that angle is going to be slightly less than 109.5. So we've got 2 more to look at. Let's look at SF4. So SF4, again, we're going to have our 4 fluorines around sulfur. Sulfur still being our central atom. And we have a total of 7, 14, 21, 28, 34 valence electrons. And we've drawn 8. So we have 26 remaining. So we'll start by filling up our external atom. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 20, make sure I got that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we've drawn a total of, can I add? Yes. Yes, I can add. We've drawn 24. So we've got 2 left over. This is taking a second because I was making sure I meant to. I was thinking of BRF4 minus, the next shape. Okay, so we've got 2 left over, so we put our 2 on our sulfur. So now we've got a shape where if it were the electron geometry, we would call this trigonal bipyramidal. That's where we have a trigonal planar that forms in our equatorial plane. That's the thing that goes through the sulfur one way. And then we'd have a fluorine on top and a fluorine on bottom of our sulfur. But remember, we're asking for the molecular shape, so we need the name for this. So if we were to arrange this in something that looks more like the shape, we would have S with 2 fluorines on top. We would then have our fluorine that's going away from us. Then we have our fluorine coming towards us. And then we would have our lone pair here. And if we remember, we can tilt this shape and it ends up looking like a seesaw, where the 2 fluorines end up working, these 2 fluorines here, work as the base of our seesaw so that we can move our other 2 fluorines around. This is one that has a name that you may not see right away, so this is one I definitely suggest you look at, but it may be something once you've looked at it once, you're like, okay, I kind of see it. And even if you don't, it's okay just to learn the name seesaw. So we have a seesaw molecule. So for this one, we're going to have 2 different bond angles. We've got the bond angle that occurs right here between this fluorine and that fluorine. That bond angle is going to be a 90-degree angle. Then between these 2 fluorines, we're going to have an angle around 120. Remember specifically that both of these are less than because of this lone pair here pushing everything together just a little bit more. But this is the one shape where we have multiple angles combined. Any type of molecule that starts as trigonal bipyramidal as its electron geometry could have this. Now, that's not true when we get to some of the shapes. For example, if we had 3 lone pairs, it would just be a linear molecule. Then we've gotten rid of everything on the equatorial plane, so there is no more angle, a 120 angle. We just have a 180 because all we have left are whatever molecule it might be on top and on bottom and something in the middle. So remember, that's the only time we're going to see multiple angles in the same space. Will be some of the trigonal bipyramidal shapes, but not all. So let's look at the last example now, our BRF4 minus. Remember, we have to pay attention to this minus sign. That means we have slightly more electrons than we might expect if we were to just 1 more than if we just had BRF4 by itself. So I'm going to again draw a BR with 4 Fs. I'm going to assume I don't know what the orientation is. And we have 7, 14, 21, 28, 35 electrons for the neutral molecule. And then because it's a negative, we have 36 valence. And we have drawn 8 so far. So remaining, we have 28. For this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 6, 12, 18, okay, 24. I've skipped 2 somewhere. Make sure you do good on your counting. If you miss some, it'll make the shapes hard to name. So we've drawn 24 more electrons, so we have 4 more remaining. So that's going to put 2 lone pairs on our bromine. If we remember right, that means that the electron geometry would be octahedral. But we have 2 lone pairs. And in our octahedral shape, we take them off the axial planes first. So this removes both axial atoms. That means we only have 4 that are left that form a plane in the equatorial plane, and we call this molecule a square planar. That's because it forms a square between the 4 molecules. And our square planar is going to have a bond angle of 90 degrees. Because since they're all 4 in a plane, we divide up a square. It's got 360 degrees as well. Each of them will have to form 90 degrees because there's 4 different angles. They have to split that up. So that should cover most of the shape stuff. You should be comfortable with being able to come up with these Lewis structures and then to be able to come up with the names as well. Don't forget to pay attention to things like ions and the fact that you have to actually draw the Lewis structure so you see how many lone pairs there are. Because many times I see students that will, instead of doing that, will just look at the number and go to something like, let's say, SF4, and we'll say, oh, there's a 4 here. This must be a tetrahedral molecule because there are 4 external atoms, without first drawing the structure to check, are there lone pairs or not? So that comes up as well. So let's go to the next one. We've got one more type of thing to look at. Let's go back and think about hybridization. So for this, again, I suggest you try these problems first before I go over them. Okay, so we've got 4 examples, some of which we already did, some of which we haven't, where we ask what type of hybrid orbitals are present in the following molecules. And below I point out that for these Lewis structures, sometimes the problems will actually ask you questions about the molecules themselves. For example, how many double and triple bonds does each molecule have? That's a way of asking you to draw the structure without literally having to have you do it in a box and be able to make it a multiple choice question. So let's start with CF4 and ask about the hybridization. So we have a carbon in the middle, and we have 4 fluorines. So again, we have 7, 14, 21, 28, 32 electrons. We've drawn 2, 4, 6, 8 of them. We have 24 remaining. We'll start putting them on the fluorines. And when you get this through, you will find out that adding full octets to each fluorine gets you exactly to 24. And then our carbon's already content with 8. So we're good. There's no double or triple bonds in this question. So if we were asked how many double bonds and how many triple bonds are there in CF4, the answer would be 0. Now let's go to the original question. What type of hybrid orbitals are present here? Our carbon is going to be sp3 hybridized. Remember, that's because there are 4 domains here. So those 4 domains let us know that if we have S, P, 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 D, D, it's going to be the 1, 2, 3, 4. The first 4 of these. Note that you can also just remember that this is sp3. That's fine too. Also, in case anyone's here from somewhere else, we're not worried about, for this course, about any of the hybridizations that are not just traditional SP, SP2, SP3, SP3D, SP3D2, where you hybridize some of the P's and D's together without the S or anything like that. We're not worried about those types of structures. Okay, let's try another one. And this is also to mention for the class, if you go and Google hybridized structures, you will see some others other than what we're saying. So we're giving you the most straightforward rules for the molecules you're going to deal with. So let's look at another one. Let's look at CO2 now. So for CO2, we get C, double bond O, double bond O. And I'm doing this because we've done this structure so many times. But if you don't remember how to do it, I suggest go back and do the traditional hybridization. Also, make sure you know how to do formal charges to know that the double bond structure is the best resonance structure. And I'll do a quick review in case we don't remember formal charges at least. So, a formal charge is where we take how many electrons would this valence atom have normally by itself. An oxygen would have 6 valence electrons. We then subtract how many lone pair electrons did we draw? That was 4. We then subtract how many bonds we drew. That was 2. This is because the oxygen is only going to get credit for half of the electrons from our bond. So each bond has 2, so by counting how many bonds, you're giving it half of them. This gives us a formal charge on the oxygen of 0. You get a 0 here. The same happens on the oxygen on the right because this molecule is symmetric and all these numbers remain the same. We then have to do the carbon. So the carbon would normally have 4 valence electrons. It has no lone pairs, and it has a total of 4 bonds drawn. So it also has a formal charge of 0. These formal charges mean that our molecule is our most stable possible resonance structure because the formal charges overall add up to 0, which is our best structure. If you had drawn the triple bond, single bond structure, you end up with some non-zero formal charges, which makes it a less good resonance structure. Although still a structure you can draw if you're asked to draw all the possible resonance structures for carbon dioxide. So, now if the question were to ask us how many double bonds are there in carbon dioxide, the answer would be 2. We can ask us what type of hybrid orbitals there would be. The carbon, our central atom, is going to be made up of sp hybridized orbitals. This is because there are 2 domains here. Remember, our double bonds don't count for extra. We only count them as 1 domain. So we have 2 domains total. So that was for our sppddd. We had 2 domains. So that got us to sp. Now let's try looking at our carbon monoxide. So carbon monoxide, we're going to start with C single bond O. We have a total of 10 possible electrons. Because there's no central atom, because you have 2 external atoms basically, we can start on either one and we'll get the same answer. So we've drawn 2, so we have 8 left. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Clearly, carbon doesn't have enough electrons. Its only choice is to ask for oxygen to share. Because carbon sharing just removes more electrons from it. That doesn't do any good. So it's going to need a total of 4 more electrons because it's missing 2 pairs. That means we're going to need to move both of these lone pairs into the bond. This is going to give us a carbon triple bonded to an oxygen, each with 1 lone pair. Now for the hybridization on this, we can answer for either the oxygen or the carbon. It'll be the same. Both are sp hybridized. This is because there are 2 domains. There is the bonding, this 1 triple bond domain, and then there is 1 lone pair. And this is true for both the oxygen and the carbon. Remember, don't forget to count the lone pairs as part of your hybridization, but only for the atom you're concerned with. So usually the problem will ask about the central atom, or in this case, we can ask about either the carbon or the oxygen because they're the same. Also, for our below question, this problem would have 1 triple bond. It's a way they know, did you know what the structure was? They could also ask about how many lone pairs are there on the oxygen, for example. And then you need to tell them there is 1 lone pair, or there are 2 lone pair electrons. In general, just make sure you're reading what's the exact question they ask. For example, did they ask about the number of electrons or the number of electron pairs? Those numbers will be different. So now let's do one more, and then we'll be done with this. Let's do SF6. So, for our SF6, we've got sulfur bonded to 6 fluorines, which this one we already did on the previous slide, so I'm not going to worry about having to count all the valence electrons. We'll just go with the fact that yes, there are indeed octets filled for each fluorine, and that uses up the valence electrons exactly. Okay. So there would be no double or triple bonds. And then if you had, I don't think we'd ask lone pairs on this for lone pairs of the fluorine because that would be a lot. But maybe they would ask about lone pairs of the sulfur. There's no lone pair electrons on the sulfur. We could also ask how many single bonds are there? There are 6 single bonds. It's a way of knowing there were no double bonded species. Okay, so from that, we then want to answer the question, what's the hybridization? So this has a total of 6 domains. So you can either just remember that's sp3d2, or we can remember our sppdd, 1 domain, 2 domain, 3 domains, 4 domains, 5 domains, 6 domains. We have the sp3d2. So hopefully this either refreshed your memory where you feel like, yes, I remember how to draw Lewis structures, and I remember the names for these, and I remember their hybridizations and their angles. Or maybe a few of those things I just said, you went, I didn't really remember that. Like maybe you remember the names for the structures, but the angles or something, you're like, I really don't remember that. That's why I would suggest to choose which of those you didn't remember very well and go back and look over those some. Hopefully they'll feel familiar because you've done them in class, and a short refresher will help you to do those problems much more easily.